Yeah, we gain electrons, right? We're reducing the charge because we're gaining electrons, right? Does anyone remember the acronym for how you remember reduction and oxidation? Does it do with oil? Oil rig, right? So you have oxidation is loss and reduction is gain, right? So oil rig reduction is gain and oxidation is loss of electrons. That's how you can remember which one is which. We can also think of it in terms of other atomic species, right? So oxidation, the name actually comes from gaining oxygen, right? So when a compound gains oxygen, that's the same thing as losing electrons. Or if we lose oxygen, that's the same thing as gaining electrons. Or you think of it, oxygen is a very electronegative element. When it bonds to something, it tends to pull electrons away from that species. The opposite, when oxygen leaves, the electron density tends to move back onto that species. We can also think of things in terms of hydrogen, right? So we can reduce or oxidize organic, purely hydrocarbons, compounds that are only made of carbon and hydrogen, just by removing and adding hydrogen as well. So hydrogen follows the same trend as electrons. So gaining hydrogen is reducing and losing hydrogen is oxidation, right? So there's a couple other ways that we can think of oxidation and reduction. And so we looked at breaking down redox reactions into their half reactions. And what were the half reactions for these reactions? We had two different half reactions. What did each half reaction represent? What were the half reactions? What was one half reaction?
Is it the one that one reaction loses electron?
Yeah, well, it's your oxidation reaction. The other one is your reduction reaction, right? We're looking at specifically the movement of electrons in the reaction, right? We have a 1/2 oxidation reaction, and that's like we have metal A goes to A plus plus an electron, right? Where we've lost an electron. That's our oxidation half reaction. And then we have our reduction reaction, and that was metal B plus goes plus an electron goes to B, right? We gain electrons in the other reaction. And this is to look at the overall movement of electrons. And ultimately this is going to be important because the movement of electrons is going to determine the potential of a cell or a redox system. And then that we're going to be able to use ideas in thermodynamics to understand that, right? So that's why we looked at that. And we looked at balancing both of these reactions in two different systems, right? We had acidic solutions and then basic solutions. Right, we had acidic and then we had basic solutions because we needed to make sure that the charge on both sides of our redox reaction is conserved and the mass is conserved on both sides, right? And so the basic or acidic solutions is what allows us to really balance the charge, right? And we do so, and we can balance hydrogens and oxygens in this method too, because oxygen and hydrogen is also how we can define reduction and oxidation, right? So the movement of oxygen and hydrogen also is important for reduction and oxidation. And so in acidic solutions, how did we balance right? Balancing the electrons is easy, right? We just multiplied the equation by whatever coefficient to make sure that in our redox reaction, the electrons on the reactant side cancel with the product electrons in our oxidation reaction, right? So that's just multiplying the equation. How do we balance the oxygen and hydrogens and the charge in these reactions in acidic solutions? What did we add? The first thing we balanced was oxygen. We balanced oxygen first. how do we balance oxygen in acidic solutions?
So you would add water to balance oxygen.
Yeah, you add water to the electron or the oxygen deficient side. And all that means is it's just a way of saying you add water to the side that needs oxygen to balance the equation, right? We plus H2O to the oxygen deficient side, to deficient side. And then we balanced hydrogen after, right? And how did we balance hydrogen in acidic systems?
You add H plus.
Yeah, you just add hydrogen ions, right? Because acidic solutions have free protons to get rid of, right? So we just add H plus to the H deficient side. And when we do this, we end up balancing the charge of both our half reactions, and we make sure that the oxygen and hydrogens are also balanced, right? Because when we add water to the oxygen deficient side, now we have to account for that by adding hydrogens to the other side. And what about in basic solutions? How do we balance oxygen?
You would add water to balance oxygen.
So we're going to add water, but we're also going to add something else to the other side whenever we balance according to in a basic solution, right? Because we want to make sure that we can't just add hydrogen to the other side, so we want to make it hydrogen neutral on both sides.
So you would add hydroxide.
You add hydroxide, you add 2 hydroxides to the oxygen deficient side, and 1 water to the oxygen, not efficient, but the side with all the oxygen, right? The side that you're trying to match the other side to. So you add 2 OH minus to oxygen deficient, and then you add H2O to the other side. Right, because if you add 2 hydroxides to one side, you've added 2 hydrogens, 2 oxygens, you add water to the other side, you've added 2 hydrogens, so that's hydrogen neutral, right? We haven't added any net hydrogen to the equation, and you've added 1 water, right? So there's a net surplus of 1 oxygen, so there's a net surplus of 1 oxygen on the deficient side. All right, so that's how you balance the oxygens. And after you balance the oxygens, then you balance the hydrogens again. So this, sorry, if you're having trouble reading that, that's other to the other side. Is that what you're trying to see? This one right here? Yeah. Other? Okay, yeah, that's you add water to the other side, right? So on reactant side, for example, the reactant side is oxygen deficient. You add 2 hydroxides. To the product side, you would add 1 water. All right, so the nice thing about balancing half reactions compared to normal chemical reactions is there is a formulaic way to go about it, right? Normal balanced chemical equations, right, it's a little bit of an art. You kind of have to, after enough experience doing it, you kind of see how you should start balancing certain things first, but there's no universal method for balancing all equations, right? There's always going to be a scenario where there's going to be some trick involved too. To balancing in any method that you use to balance those equations, there can be one exception or so to the rule. For half reactions, it's always going to be this method of balancing for redox reactions. It's always going to be this method of balancing them in acidic or basic solutions. All right, we can always balance oxygen or hydrogen based off of the type of solution that it's in. So how would you balance hydrogen then? Thank you. You add 1 water molecule to the deficient side, to the H deficient side, and then what do you add to the other side? How would I have a net hydrogen on the deficient side? You add one hydroxide to the other side, right? Because now we've added one water to both sides, or one oxygen to both sides. So there's no net oxygen added. We've added one hydrogen here and two there, so there's one extra hydrogen on that side, right? So that's how we balance those. And once you've done that, you're done and you've balanced your redox reaction. And that's because water and basic hydroxide ions or H3O plus are involved in your redox solutions, right? These are ions that carry charge, and so they help move electrons around. They kind of stabilize that process. So that's why they're involved in there. You add your two half reactions together and you get your net redox reaction. All right, any questions about where we ended with last time, right? So last time we talked about the general formulation for what is a redox reaction, what are the half reactions, and then how do we balance these equations, right? Any questions on that? Right, so the practice exam has another example of which the practice exam is already posted. I forgot to put that up there, so make sure you look at that before the exam on Tuesday. So even if you're doing the project, you still have to take the exam. That's just a check mark to get credit for doing the project, right? Okay. No questions? All right, and so what we're going to start with today and what kind of leads to the thermodynamics of electrochemistry are electrochemical cells, and we have two types. We have voltaic cells. These are where we have spontaneous redox reactions that generate electrical current, right? So you're going to have a cathode and an anode. Those are your two components. They're going to be connected by a conducting wire. And at one side of the voltaic cell, the anode, for example, you're going to have an oxidation reaction going on, which means that's feeding electrons into the wire. Then at the other electrode, the anode, you're going to have a reduction reaction going, meaning it's taking electrons from the wire. And so what happens is you're going to get a net current that moves through the system. If the reaction is spontaneous, meaning it happens spontaneously on its way to equilibrium, then you call that a voltaic cell, which is a battery, right? So that's how batteries work, is we separate things based off of electrical charge and concentration, and then we let current run through the system, and that's what charges your system. And so these voltaic cells, there's been the most efficient one right now. Does anyone know what the most efficient battery system we have is? They don't allow on airplanes. They try not to tell you on airplanes. They ask you when you go to TSA. Lithium-ion batteries, right? Lithium-ion batteries are very efficient because they have a very large potential difference, and they have the least degradation out of most other batteries. And that's, for example, what powers electric cars too, is very large lithium-ion battery banks. So there's also research being done in voltaic cells for solid-state batteries, right? So right now you can look at our voltaic cells, and it's going to be a solution reaction that's happening. A solid-state system is where you have a solid solution, right? Not the electrolyte, but what carries the electrolyte is going to be a solid, and the benefits for that is that you don't have as much degradation at the cathode or anode, and that allows those batteries to stay efficient for longer. So, and if anyone's heard of Toyota, they've put a good amount of research into solid-state batteries. The only downside to solid-state batteries is if they're brittle or fragile and you hit a bump and your battery cracks, now you have a huge defect in the battery, it wouldn't work as well. But those batteries, for example, are looking at cars with mile ranges of 500 to 700 miles per charge, right? Which is, about 2 to 3 times as much the current electric car standard. So those are going to be cells where the redox reaction is spontaneous, right? And so we're going to look at how does the potential difference across that cell lead to spontaneity. And then the opposite is going to be electrolytic cells, where you have a non-spontaneous chemical reaction or redox reaction, and you can flow a current through the system and then cause the non-spontaneous reaction to happen. So an example of this is if you're doing electroplating of metals, for example. So sometimes people do this in physics, the physics 3B, I believe it is. So electricity and magnetism is one of the labs early on, is you have a copper electrolyte and you put a little current through the system, and then that causes copper to deposit on the electrode, right? Because if we look at some of our redox reactions here, see, do any of them actually have the state of matter here, right? So if we look at the state of matter here, we start with stuff that's in the solution phase, and this is going to be, something that's deposited on the electrode or where that reaction is happening. So if this is a non-spontaneous process, meaning delta G is what sign? If it's non-spontaneous?
Greater than?
Positive, right? So if this is positive, you then generate an electric current, you flow it through the cathode or the anode, and then that allows this reaction to happen, and this happens at the cathode or electrode. This solid will get deposited on the anode or cathode. And so in electrolytic cells, that is one example of a non-spontaneous process. Another one is water splitting, so you can break up water into its constituent atoms, so hydrogen gas and oxygen gas, and then if you were to recondense that water in the spontaneous reaction, that was one way people are looking into purifying water. The reason that you don't just do that, even though it's very feasible to do that, is because it requires generating electric current and putting it through a system, right? So if you're putting current through the system, that takes energy. Energy usually comes from burning of fossil fuels, so then it ends up not being that efficient and a net negative for everything. It's cheaper and more environmentally friendly to just pull water from the ground, right? So that's another example. Also, if you've seen, I was talking, Noe's not here right now, but I was talking with Noe. If you've seen the trend in water where they want hydrogenized water, has anyone seen those? They have these water bottles, you press a button, and it starts making bubbles in the solution. All that's happening is the batteries are putting a current through the system, and it's splitting water into hydrogen gas. And the idea is you dissolve hydrogen gas in your water, and then it makes it more healthy for your body. But there's no evidence that that's true, but that's one of the examples of an electrolytic cell right there. And so it's pretty widely available. Actually, my mom is really into that kind of stuff, so I should have brought it in today to show you guys. It just makes a little vibrating noise, and you see little bubbles going out. It's a cool science experiment, but not that healthy for you. It's not bad for you, it's just you're drinking water, so that's good, I guess, right? All right, so those are two types of electrochemical cells, right, or galvanic cells. Voltaic cells and electrolytic cells, right? So here we have a voltaic cell. Each half cell is made from a metal strip that dips into the solution, right? So this is where we have each of these are what we call our electrodes, right? So this is how we would define our electrodes. And then usually there's a wire that connects these two. And the space in between these, this is called a salt bridge. And the purpose of the salt bridge is usually to neutralize charge in the system, right? So you can imagine that if you let the redox reaction go on, even if it's spontaneous, eventually you're going to get a buildup of charge across the cell. And what happens is if that charge buildup gets large enough, it reaches a state of equilibrium where now you want electrons, let's say, to flow from the cathode to the anode, right? They flow from positive to negative because current is defined backwardsly for whatever reason. They flow in this direction. If this is then the anode where the reduction reaction happens, so you're taking in charge from this side. Here you're losing electrons. You're going to get a buildup of your copper plus here because you're losing electrons to the cathode, and here you're going to get a buildup of neutral zinc. Eventually the charge difference is going to be so large that electrons are going to want to flow back in the opposite direction to then neutralize this huge amount of positive charge over here. And so what you have usually is you have what's called a salt bridge in the middle. And what the salt bridge does is it just carries charges from one side to the other, right? So it's usually made up of some sort of electrolyte solution. You can think of something like sodium chloride, and that'll then move the ions of the negative charge over here, and the positive charge will move to the other side, and that'll neutralize the charge difference across the cell. Then you're just relying on the spontaneity of reaction to allow the potential difference to stay zero between the two. And so eventually you will still get a buildup of charge on one side, and that just means that you have to charge your battery. Now you run electrical current through the system. The reverse reaction can happen, and then you charge your battery that way. And so a cell cannot operate, like I just said, if there exists a charge differential between the two sides, right? So the charge differential, that means that if the charge buildup gets so large, then the electrons are going to flow in the opposite direction because you've essentially reversed the polarity of the voltage difference, right? The negative side becomes the positive side, and so on and so forth. And so then you have the salt bridge, and between the salt bridge is filled with charges that then do not interfere with the redox reaction. So that's an important part, is that they do not interfere with the redox reaction, meaning they don't react with the species. They're just neutral ions in solution. And so they can just move back and forth to help neutralize the charge. So you get a lot of positive charge. Well, now my chlorine ions are going to move over to that side to neutralize all the charge there. Then I'm just relying on the spontaneity of that reaction happening. And so this process then equalizes the charges built into the two half reactions. Again, that concentration is finite, so you will eventually still need to reverse the reaction to fully get your original amounts of each of your redox species. But this allows your battery to then last a lot longer when you have this salt bridge in there. And so sometimes you have a bridge like this that exists, but for example, in your lithium-ion batteries, you have usually the equivalent of, does anyone remember what an amphoteric material was in acids and bases?
It could do both. It could act as a
acid or a base, yeah. So usually your electrolyte that you have in your battery is something that can both neutralize positive and negative charges based off of the form that it's in. So that's usually the type of salt bridge that you have, right? You don't have a little bridge in your lithium-ion batteries that allow ions to move forth. You have an electrolyte solution that's going to help neutralize the cathode and anode. If you think about your lithium-ion batteries, they're very, very thin, right? So it's almost like a capacitor that has an electrolyte solution in between there. Capacitor is just two oppositely charged plates. Right, so that's how we have voltaic cells, right? And so in our voltaic cells, we have the reduction reaction at the cathode, right? So in this case, this would be our cathode. And so the way to remember that is red cat, right? So our reduction reaction happens at the cathode. Our cathode is going to be positively charged, right? Reduction, oxidation, right? Oxidation creates cations. Cats make the professor happy, so those are positive, right? So that's how we remember that cathodes are positively charged. And then where does reduction happen? Well, it happens at the red cat, right? The reduction happens at the cathode. And right, the anode is going to be negatively charged. That's where we have our anions present in solution. That's going to be where our oxidation reaction happens, and we move from the anode to the cathode. So we move from negative to positive. Electron flow, so if you've taken electricity and magnetism, one of the interesting things about E&M is that the electron flow is opposite to the current direction, right? So we define the current in the opposite direction of electron flow. So the current goes in the negative direction of electron flow. Electrons flow, however, from where oxidation happens, right? Because oxidation, we're donating electrons. Where are those electrons going? They're going into the current carrying wire, right? So this electron goes in through the wire, and then they meet at the cathode, where then the species gets reduced, right? The electrons move through here. We have a surplus of electrons at the surface of the cathode. So now our copper ions, in this case, they're present in copper 2+ in solution, so they come, pick up an electron, and become copper solid. That means that this cathode is also going to be where we have deposition of copper in this case. For most modern day voltaic cells, you do get buildup of some solid, but it's not going to be deposited directly onto the electrode. Usually you have things that stay in the solution phase, and you have very porous materials. So the people that just won the Nobel Prize actually they won it for what are called metal organic frameworks, right? So they have a framework of both carbon-based molecules and metals. And those are very popular for making electrodes right now. Why? Because they tend to be very porous materials, so they have very small nanostructures. If you know anything about nanostructures, that means as the structures get smaller, their surface area gets larger, right? So larger surface area means more possible reduction reaction or oxidations happening at the cathode, means you have more efficient transfer of electrons. And they last longer because you can have that redox reaction happen at a faster, for a longer time, because there's a lot more surface area for that to happen. Right? If we're depositing copper ions, as a simple example, or copper metal atoms, if you have a larger surface area, you have more places to deposit it, copper metal ions. All right, so anode is where the oxidation reaction happens, and then red cat, the reduction reaction happens at the cathodes. Electrons flow from negative to positive, but the current is defined in the opposite direction because they wanted to make it confusing. All right, any questions about voltaic cells so far? No? Okay. So when you're sketching and labeling a voltaic cell, you're going to consider the following things. So the electrodes, right? The anode is a more negatively charged electrode because that's where oxidation happens, where the species is reducing electrons, and it's usually labeled as minus. The cathode is a more positively charged electrode and is labeled plus. Electron flow happens away from the anode towards the cathode, and that's where the oxidation happens at the anode, and the reduction half reaction happens at the cathode. All right, so again, I'm going to put red cat here and ox. And so you might ask, well, how do these voltaic cells actually work? Like, how do we know that if they are going to work, or are they going to be spontaneous or not? Is we look at the activity of each of these reactions, right? And so these are both our redox reactions. And we look at something called the activity, right? And the activity is usually measured. Does anyone remember what activity is usually measured from? Activity is usually somewhat related or directly related, proportional to the potential of the reaction. And this is the electrical potential, right? So it's usually given by delta V. Delta V is how we define the electrical potential. This is analogous for mechanical systems where you have delta U. U is usually the potential energy. Delta V is the electrical potential, is how we define it. And so the activity is related to the potential. And usually how these are tabulated is they're tabulated in standard reduction potentials. And what that means is if we have a oxidation reaction or a reduction reaction, right, we have a difference of charge as this reaction happens, right? So there's going to be a difference of charge if we have one species being oxidized and one being reduced. The net charge on both of these reactions is neutral, for example. But you can have a difference of charge, and how large that difference of charge gives us something that's related to the potential, and that value for the potential tells us which one is more active, right? So if we have a redox system, one of these is going to have a larger or smaller potential compared to some standard. And when they do, that means that species is going to be more likely to be oxidized or more likely to be reduced. And so these are inherent properties of the metal, right? So these are inherent properties of the metal. And so when we look at modifying redox reactions, so when you're balancing your redox reactions, you look at the half reactions and you look at their standard potentials. And because these are inherent properties of the metal, we can define two types of variables in thermodynamics. One is going to be an extensive property of the system, and one is going to be an intensive property And an extensive property of the system just means that this property changes with the system size, right? So this would be something like delta G is an extensive property of the system. If the reaction happens more, the change in Gibbs free energy is larger, right? Because there's a certain Gibbs free energy associated with each reaction. So the more reactions happen, the larger that energy difference is. An intensive property is going to be something that doesn't change with the system size, right? So the potential difference from a redox reaction compared with some sort of standard, the same way we talk about state functions being compared to the zero value, and we set that zero arbitrarily. When the reduction of this reaction is compared with that potential, you get a difference in potential. That doesn't change based off the number of reactions that happens. That standard potential is always the same. So that would be an intensive property, right? So this does not scale with system size. So this is something like delta V, temperature. Actually, I lied, temperature does scale with system size. And extensive properties are things that scale with system size. This is like the internal energy, the internal energy, Gibbs free energy, the entropy of the system. All of those are going to scale with the size of the system. Meaning the more that's happening, basically if you can convert that quantity into a unit of per mole, then that means it's an extensive property. If you do not have any units per mole there, then it would be an intensive property. And the reason I say this is because when we determine standard cell potentials and things of that nature, it depends on the modification of the redox reactions, but we're not going to change the values for the standard reduction potentials for these systems. And so because each of these different electrodes are going to have different activities, in this case, this means that it said the copper, I believe, right? It said the copper, or the zinc is more active than the copper. That means that the oxidation reaction is going to happen at the anode, and then at the cathode, you're going to have the reduction reaction. So the values of the standard potentials, values of delta V, determine what is being oxidized and what is being reduced. And so the standard potentials then tell you what is the anode and what is the cathode, right? So this is another way of saying what is the anode and what is the cathode for the system. Right, so one of the things to be able to do for electrochemistry is to look at your redox reaction given a set of standard potentials. So today we have a dry lab. We might start working on it in lecture and then continue it in lab. A lot of it is going to be determining which one is going to be the anode and which one is going to be the cathode. And so the next couple slides are kind of just stating things that I've already said, right? So we see that we have an internal connection. This is called what again? In between there, what helps neutralize the charge? The salt bridge, right? So this was our salt bridge. And so this is just in words, saying what happens in the previous picture. Then the system where we have all of the flow of these different ions, right? We have things that are, we have the salt bridge then balancing charge, right? As we have things being deposited, positive ions being deposited, the copper on this side, the salt bridge ions will flow to the other side to counteract the buildup of the positive zinc ions that are being made in solution. And then vice versa, the positive ions in your salt bridge, so like your sodium ions, are moving the other direction to help neutralize the charge in this solution. Right, and why do we do that? Well, if we allow charge buildup, that charge differential, and the way we can think about this is, delta G, we can do a sequential series of steps that we know how to change the Gibbs free energy of the system. If we have different concentrations, we know delta G is related to equilibrium constant, so it's related to the concentrations. We also have a term that's related to the charge differential. So if those two things are fighting each other, eventually they'll reach a state of equilibrium where they won't have any reaction happening anymore. And so this salt bridge, again, helps the system reduce how fast or how often it reaches equilibrium. And so the kind of way to represent these voltaic cells is called electrochemical cell notation. And all you have here is you have the two different species being oxidized or reduced in both of these reactions. They're separated by the double line, which means the salt bridge. I know I have that there, but this is the salt bridge. And the cathode is on the right side. The cathode is where reduction half reaction happens. And you're drawing the species, or you're just writing the species that is being reduced in this case, right? Copper is in the aqueous state originally. It's getting deposited on the cathode, where it picks up 2 electrons and becomes solid metal copper. On the anode, right, we have the oxidation half reaction. So this would be the oxidation half cell. This is going to be the more active metal, right? So it's going to be the more positive reduction potential. We'll talk about that in a second. And it's the same thing. We start with the zinc solid. This is where oxidation happens, so we end with zinc 2+ ion, right? So the unoxidized version of the metal and the oxidized version are separated by a bar on the cathode, the anode. They're separated from the cathode by a salt bridge, which is just symbolized by a double bar. And then the cathode, where the reduction reaction happens, we have initially copper 2+ ions in solution. It picks up 2 electrons in the reduction process to become solid copper. And then it's separated by a bar, right? So the reactants and products are separated by a bar. All you're doing here is you're just ignoring the movement of electrons, and you're also ignoring the presence of water and hydronium or water and hydroxide in solution. You're just looking at the species that are being oxidized or reduced in our system. Right, so being able to be given an electrochemical cell notation and write the half reactions is important, right? So what would be the half reaction for this side? On the left-hand side there. How would you actually write that half reaction?
Would it be, maybe Zn minus 2e, and then it...
Yep, it's Zn minus, or not, Zn, yeah, plus 2e, right? We don't write minus because this is saying...
It's an
it's actually, sorry, I like. So this is going to be zinc. If the same thing as writing minus 2e is adding plus 2e to the product side, right? So the half reaction for this side, the half reaction is zinc solid goes to zinc 2+ plus 2e, right? Where do these electrons go in our electrochemical cell? Do the electrons just go and float around its solution? What is our electrochemical cell, our voltaic cell, used for? So the salt bridge is going to have its own ions. that are present, right? So the two solutions are connected by a salt bridge. What else connects the two electrodes? Or if you think about an electrical system, what should connect your two electrodes? Think about does anyone know how the first batteries were made? Redox reactions connected to potatoes and lemons. Right, and what did they do? How did they show that these worked as voltaic cells? If you were to design a system, what's the simplest way you could say, is there current or is there not current flowing through the system? Same thing as if an idea suddenly pops in your head.
Light bulb.
Yeah, you test a light bulb, right? So if you test a light bulb, we put a light bulb in between them, right? And the light bulb lights up. Oh yeah, there's electrical current going through, right? You have a little filament, there's electrical current going through, high resistance, it shines light, right? So what connects the two electrodes then, right? You can't just have a light bulb floating above your voltaic cell. What does the light bulb have to be connected to each of the electrodes? It's going to be connected to a conducting wire, right? So something that's going to carry the electrons. So these electrodes that are being deposited at the anode, they're not just going and floating around in solution. They're going through the wire, and that's what's generating, we have movement of current moving through the electrical wire to then go to the cathode side, where then the other half reaction, what's the other half reaction in this case? Right, the cathode, what happens at the cathode?
The electrons go into it.
The electrons go into it, right? What type of half reaction happens at the cathode?
Redox.
It's half of the redox reaction. The reduction reaction happens at the cathode, right? We have the reduction reaction, and so that is copper 2+. And then how do I write the reduction reaction? Plus two electrons. Now, because we're picking up the electrons from the conducting wire that's carrying the electrons, and that goes to copper solid. Right? So these need to be connected by a conducting wire because that's what carries electrons over to the cathode, to the less active metal, where the reduction is going to happen now. All right, and we have to be able to look at the cell notation because this is how people still write batteries if they're designing batteries. Even for lithium-ion systems, they have the lithium-ion batteries described in cell notation. Of course, it's not as simple as just two metal strips like this, right? The lithium-ion batteries are usually complex ions that have one or two components, so it looks a little more complicated than this. But if we do have other products or reactants on either side of this reaction, all that changes is we just add a comma and add whatever the product or the reactant is, right? So if, for example, we had nitrogen monoxide and nitrous on one side and then nitric acid on the other side, right? Those things, how that would move, you just add a comma for whatever's on the product or the reactant side. So if there's multiple species here, just add a comma and then the other reactant there. Bar, whatever the products are. The only thing you're ignoring is you're ignoring the explicit movement of electrons in the half reactions, and water and hydroxide or hydronium. Okay, let's see. We have about 2 minutes. All right, so if we have a complicated reaction here, right here we're looking at an iron system that's being, let's see, the iron in this case, what's being oxidized and what's being reduced? All right, so this is a pretty large system. This is a balanced redox reaction. So when we talk about balancing redox reactions, this is what you would look like after it's been balanced, right? We use water to balance the oxygens on both sides, right? That's why we have 8 waters here, because we have 8 oxygens there. And then we use the hydrogen ions to balance the hydrogens, right? So because we added water here, the H+ ions are important. I think I misspoke a second ago. I said you ignore the hydronium or hydroxide, but those you keep in because those are also involved in the charge neutralization.
The left side being reduced?
And so we have the total redox reaction here, right? Which means something's being reduced and something else is being oxidized, right? So what is the charge number for solid iron here? 0, right? Because it's neutral iron, right? We haven't lost or gained any electrons yet. What is the charge on iron in the product side of this reaction? 2 plus, right? So what happened to the iron? It was oxidized, right? Because it lost electrons. So iron is oxidized. And the other species we're going to look at is the manganese oxide. Why don't we look at oxygen here in terms of oxidation or reduction? Why don't we check to see if oxygen is reduced or oxidized? Does anyone remember? I mentioned it briefly at the end of last lecture, or lab lecture. All right.
Is it because it's in the water? Or like the oxygen goes?
So because we're balancing it with water, that tells us something that we actually, it's not important in analyzing the oxidation state of oxygen. It's along those lines, but that's part of the treatment of it is because of water, right? We treat it with water because we don't look at the oxidation state of oxygen. But why don't we analyze oxygen, right? So we know we're looking at what's happening to iron here. How come we don't look at, and we're going to look at what happens to manganese, but we're not going to look at what happens to oxygen. Why is that? What are the different ways we can define oxidation and reduction? All right, so what is oxidation? Loss of electrons. And what was another way that we could define it? Where does oxidation get its name from? Oxygen, right? We're gaining oxygen or losing hydrogen, right? The reason we don't look at hydrogen or oxygen in terms of their oxidation state changing is because it would be like asking, well, is the electron oxidized or reduced? Those are part of the oxidation or reduction process. The movement of electron can be analyzed in the same way as the movement of oxygen or hydrogen as well, right? So we wouldn't say an electron gets oxidized or reduced, and because of that, we're not going to say that a hydrogen atom or an oxygen atom gets oxidized or reduced, right? At least in the analysis of redox reactions. So we're not going to look at oxygen in terms of is it gaining or losing electrons, because it's always going to have an oxidation number or a charge number of -2, and hydrogen is always going to be what? +1, right? So if we have 4 oxygens there, what's the total charge associated with that? Yep, that's -8 here. And what's the total charge on this molecule? -1, right? Because this has a -1 charge here. So this is -1. So what does the charge on the manganese need to be in this reaction? +7, right? We know the total charge is -1, and we get -8 from oxygen, and it's always going to be that number, right? Oxygen is always going to be -2. So we need a +7 here to then give us a total charge of -1. So that means that this is +7. What about in the product side now? What's the charge number on manganese? +2, right? Because it has a charge of +2, right? So in this molecule, yep, the total charge, right? It's not bonded to anything else in this case, right? So the total charge is just whatever the charge of the manganese is here. It's just manganese ions floating around in solution. So the total charge is going to be +2. So what happened to manganese? It was reduced because we started with a very positive charge on it. We gained 5 electrons, and now it's a less positive charge on manganese. So manganese is reduced, right? So now, if we want to write the electrochemical cell notation for this, right? Iron is oxidized, so what side of the electrochemical cell notation should that be? the left side because that's where the anode is, right? And ox, this is going to be on the anode side of the electrochemical cell. And then the manganese is going to be where? Yeah, it's on the cathode side, right? Red cat. So that's going to be the cathode. So the first step was, okay, which is being oxidized, what's being reduced? Once we know that, then we can look at the movement of electrons in each of these cases. Okay, then everyone's still writing, can I move on? Right, so the half reactions then, since this is being oxidized, is iron plus, goes from iron 2 plus to plus 2 electrons because it's losing electrons. And then the half reaction for the reduction process, to make sure that charge is conserved, is manganese for manganese minus, or manganese 4 oxide, or manganese 7 oxide, plus 5 electrons because we're gaining electrons, plus the 8 hydrogens to balance the charge, gives us the manganese 2 plus ions plus the 4 water molecules. And so if you wrote this out, this would be the unbalanced half reaction, right? That's the thing to notice here. All we did was we just divided everything in the reduction process by 2, right? Divide that by 2, we get 1. Divide this by 2, we get 8. Now we're writing the explicit electrons here, right? So we gained 5 electrons because we're looking at the specific number of electrons for each reaction. And then we, the number of hydrogens, again, divided by 2 is 8. And then this divided by 2 gives us a coefficient of 1. Divided by 2 gives us a coefficient of 2. This is the unbalanced half reactions. And so the electrochemical cell notation is then our anode, where the oxidation reaction happens, right? We have iron, goes to iron 2 plus. Then we have the manganese oxide and a hydrogen ion, goes to manganese 2 plus. This is our cathode. And the only extra thing that we have here is if there is present a electrode that acts as a catalyst for this reaction. So this is how most redox reactions are done. We don't just have copper plating and zinc systems. So why might it not be useful to have the redox reaction that we had before with the copper and zinc? Why wouldn't we want a metal, catalyst / electrode where the reaction can happen instead of the electrode being made of our specific redox reaction? Right, so this is our electrode / catalyst for the reaction. Why might we want that? And is it might okay to go back a couple slides just to show you a picture? Right, why might we want a system where the electrode isn't involved in the reaction here? If we look at something like this. Right, these reactions keep happening. What's the issue you might see? Right, in this metal on the zinc side, we have zinc ions that are constantly being taken from the anode, and on this side we have copper ions that keep being deposited as the cathode. Why might you want an electrode that isn't made up of the material for the redox reaction? What can you see specifically happening on this side? Eventually, this reaction ran on forever. Yeah, you're running out of electrons because eventually, and that'll happen for most redox systems. But if you look at this, your electrode will eventually disintegrate. Right? If this keeps happening, eventually everything's going to go into the aqueous phase. And then if everything's in the aqueous phase, you will not be able to recharge your battery. Why? Because then you don't have anywhere for the electrons to deposit and attach to the wire anymore. Right? So you want an electrode, usually that's not made from the the redox atoms or materials or species. So if you see something like this, you should be able to realize, okay, this is where the oxidation reaction is happening. This is our anode. Then this is our reduction reaction, and that's happening at the cathode, right? Or you're given two half reactions or an overall redox reaction. You're asked to balance them and then write the cell notation for that system. Okay, any questions on this right now? All right, let's take like a 10-minute break and we'll come back and we'll start looking at, with electrochemical cell, we might talk about electrolytic cells for a second. That doesn't change anything about the description of the system at all. It just means the reactions are going in the opposite direction and they're not spontaneous. We'll start talking about thermodynamics and how do we use thermodynamics to analyze a lot of these systems. All right, so I'll see you guys at 9:50 then. When we went from here, it went from +7 to +2, which means you gain 5 electrons.
Oh.
Yeah, so you're looking at the difference in charge. That's how you get that. Yep, that's where you get all of them. All the half reactions they're looking at is the movement of the electrons.
Okay.
That's the whole point of them.
Okay.
Okay. So if you have this system here, take a second to see if you can write the cell notation for the following reaction, right? So first step, identify half reactions, then write the cell notation. And you can write the unbalanced half reactions because you don't include the electron or the charge in the cell notation. What is the oxidation half reaction here? What's being oxidized? Aluminum, right? Because we start with a charge of 0 and we end with 3+, which means that we lost how many electrons? 3, right? So we go from aluminum solid to, bless you, aluminum 3+ plus 2, 3 electrons. And what about our reduction half reaction? What species gets reduced then? Zinc, right? So we write that as zinc 2+ plus what? 2 electrons, because we go from zinc 2+ to zinc 0. 2 electrons goes to zinc solid, right? So where does oxidation happen in the voltaic cell? Wait, what was the acronym to remember? It has to do with 2 animals. Anox, right? We have anox, and then what do we have? Where's the reduction happen? Red cat. Right? And it is a little confusing, right? Because the reduction reaction was the gain of the electrodes happens at the positively charged electrode, the cathode, right? So that's why it's useful to remember the acronym here, because it is kind of the opposite of, negative doesn't just stay with negative, right? The gaining of electrons happens at the positively charged electrode, right? So this is going to be our cathode, and then our anode is going to be the other one. So the way we write our cell notation is we write our anode first. So we have aluminum solid, comma, aluminum 2+, aqueous, separated by a salt bridge, right? I'm going to draw that in black just so you recognize that that's drawn in black. And then, and sorry, this is not a comma, this is a bar as well, from our reduction reaction, which is going to be zinc solid separated by a bar from, zinc 2+, separated by a bar from zinc solid. And then you weren't given anything explicit about whether or not this happened in a system with a different electrode or catalyst there, so you don't put anything else at the end of that. All right, so this would be the standard cell notation for the this redox system here. Right, so first step's identify half reactions, right? That's looking at the movement of electrons. Once you identify the half reactions, you then remember where the oxidation reaction happens, where the reduction reaction happens. That allows you to write your cell notation for the system. All right, any questions on that? Thumbs up, thumbs aside, thumbs down. All right, so let's do one more quick example, and then we're going to move through the rest pretty fast. So here you're given the cell notation for a voltaic cell, and then you're asked to write the half reactions, right? So based off the cell notation, see if you can write the half reactions for the system. And then you're also asked to write the overall reaction, right? So the overall reaction is then balancing the redox reactions, the half reactions, which in this case there's no hydrogen or oxygen or basic or acidic solution, so it's a more simple process to balance these reactions. All right, so based off of our cell notation, which one is going to be the oxidation reaction? The SC, right? Because we know that's our anode side in our cell notation, and we know that's where oxidation happens. Also, if we look at from the left side to the right side across the bar, which is from reactants to products, that also tells us that we lose 3 electrons, right? So what would the half reaction for this be?
SC goes to SC plus.
Yeah, SC solid goes to SC aqueous 3 plus 3 electrons, right? Because we lost 3 electrons. And what about the reduction, right? We have red cat on the right side, which tells us that's where the reduction happens because that's the cathode side. And our reduction reaction is what? Silver goes to silver 1 plus an electron goes to silver solid, right? So that means that in this system, silver would be being plated on the cathode, right? And we also are asked to find the overall reaction. So what do we have to do to get the overall reaction? What do we have to make sure? Yeah, that the electrons cancel. And so how do we make sure the electrons cancel in this case? What do we do to the bottom reaction? We multiply by 3, right? With the bottom reaction, we multiply by 3, so then we have 3 electrons on the product side in the oxidation reaction, and now 3 electrons, right? So we multiply everything by 3. Now we have 3 electrons on the reactant side. If they're on opposite sides of the reaction arrows, when we add 2 reactions together, they cancel out, right? So now this cancels out with that. And our net reaction is going to be scandium solid plus 3 Ag aqueous plus goes to scandium 3 plus aqueous plus 3 Ag solid, right? So this would be our overall reaction for this electrochemical cell. Right, and we see the movement of 3 electrons total for each half reaction. For the reduction, that means that you need 3 of those reactions to happen for one of the scandium oxidation reactions. Okay, any questions on that? Thumbs up, thumbs to the side, thumbs down, going from cell notation to the chemical reaction. Right, so really we're just identifying right hand side is cathode, left hand side is anode. That tells us which reaction is which, right? Okay, so now let's start getting into thermodynamics, but because we're going to start talking about thermodynamics, usually when we measure things that are absolute, like standard molar entropy and enthalpies of formation, there's usually some standard here. And so we do the same thing with redox systems, right? So we use what's called the standard hydrogen electrode. That just means under standard conditions, you're looking at the bubbling or the creation of hydrogen gas being created by a flow of electrons through an inert platinum electrode, right? So this gives us a standard potential value. So you can't measure absolute potentials in the real world, right? We don't have a way like we do for entropy to extrapolate something to some zero value. All you can do is measure the difference in potential. And so what I mean by that is if we think about, 2 water tanks that are connected by a tube at the bottom, if one has a bunch of water in there, gravity is pushing this water tank down, that will cause energy to flow into the low potential tank, right? And the flow of water into the tank with less water, right, is caused by a difference in pressure, which will push this down. That flow is the difference in potential energy between these. That flow is related to the difference in potential energy between the amount of water in both tanks. So we can think of these redox reactions in the same way, right? If we have one reaction that has a relatively larger potential than the other value, it'll cause flow of energy, which is flow of current in electrical systems, from the high potential energy to the low potential energy. And so what the standard electrode does is it gives us some absolute value that we arbitrarily design as 0, right? Since we can't measure the absolute potential of any reaction, we do it with some, in reference to some standard thing that we just set. And so chemists and electrochemists, they just decided that the standard hydrogen electrode is what would be set as the standard. So when you measure, or when you look at standard reduction potentials, all you're measuring is a standard hydrogen electrode against whatever redox reaction or system you're looking at, right? So let's say it's copper. You have the copper system here, and then the standard electrode connected through the salt bridge, and you just look at the direction of current. That direction of current tells you which one is higher or lower in value, right? If you get current flowing into the hydrogen electrode, that means that the higher potential is going to be where the oxidation reaction is happening, right? So the oxidation reaction is happening, causes current to flow towards the hydrogen electrode. That means that you have a relative larger potential energy. There are ways then you can measure what exactly that specific value is. If you have your standard hydrogen electrode, and let's say now you're looking at a system of silver, and you see that current flows from the hydrogen electrode to the silver system. Now you know that that silver has lower potential energy than your standard hydrogen electrode. You can quantify that specific difference in potential, and that's what we use as our standard cell potential values, or our reduction potentials, right? So we're always just comparing to the standard hydrogen electrode. Then, once we've compared those values, we can compare them to each other, right? Because you're saying it doesn't matter what the absolute value for 0 is, because we can always look at the difference just by subtracting those two differences from a common difference, right? So an example I used in office hours on Tuesday was you can measure distances on Earth, right, from here to Seattle directly, if you wanted to, but you can also define some standard value of distance. So let's say we look at the distance from here to Denver, right? That gives us a certain distance, and then from Denver to Seattle. The distance from here to Seattle should be the difference in distances between here to Denver and Denver to Seattle, right? So we're doing the same thing here, except we're just looking at potential energy values instead of differences and comparing them to each other, right? So we don't have some absolute zero value set, we just arbitrarily set something to zero. All right, so it's the same idea with state functions too. That's why we can do products minus reactants for enthalpies and entropies, because there doesn't necessarily matter what the absolute zero is, all that matters is the relative change. And the change can always be looked at the difference between two other standard changes. All right, so that's how we use the standard hydrogen electrode, right? So this is the reference electrode, this is everything I just said in words. If you're writing this, I'll give you a second to write while I kind of start talking about this. So once you have these standard values from some reference electrode, right, these are what are going to be the standard cell potentials for the cathode and the anode. These are the changes in voltage from the standard hydrogen electrode, or the SHE is what people define that as. Once we know these standards, then we can actually look at, well, now we don't need the standard in between, right? We can look at directly the distance from here to Seattle, right? So we can look at now the exact difference between copper and a zinc electrode. In the same way, we go from a system of higher to lower potential energy. The values of these standards, right? Let's say copper is lower than the standard higher electrode, and zinc is higher than the standard hydrogen electrode, right? If you had a system of all three connected, you would know you'd move to from the zinc to the standard hydrogen, and then from the standard hydrogen, you would move to the copper. If you just get rid of the standard hydrogen electrode, that's the same thing as just going straight from the zinc to the copper. So these values tell us the direction of current in our electrochemical cells, right? And just because they're from some reference value doesn't mean that we can't now compare them, right? The reference value just gives us a midpoint, but we can also directly compare these because we've actually assigned a value to them now. And so the difference in voltage is always between the initial and final state, and we know that our standard cell potential is now going to be defined as the potential of our cathode, right? Because our electrons flow from the anode to the cathode. So our cathode is the final state for our electrons to the anode, right? So these values are the difference from the standard hydrogen electrode. And now we can compare them for our specific cell because we don't have a standard hydrogen electrode in our cell, right? We don't need to have that all the time. We can compare how they vary from the standard. And now that gives us the total cell potential, right? And this is really just the difference in potential energy or electrical potential for the cell, right? And if we have a difference in potential energy, the same way, if a ball rolls down the hill, you start from high potential to low potential as you move down the hill, right? That's gravity. Electrical potential is the same thing. Electrons are going to move because of their charge from something with high potential to low potential. Right, so this is our high potential, high V, and this is our low V. Again, we don't have an absolute value for the voltage. These are the relative differences from our standard electrode. And so we can use this to then determine the potential for any cell. And now we can also start to think, okay, well, if this cell potential tells us the direction that current is going to flow, right, that tells us something about the spontaneity of the redox reaction. Right? That means one direction for the redox reaction is going to be spontaneous, right? If we have electrical cell potential, then we know intuitively it's going to move from high to low potential energy. And so the electrons, right, which are involved in the redox reaction, right, the electrons is actually what we're looking at, the movement of electrons, is going to be related to the spontaneity of the reaction. And that's going to be related to this cell potential somehow. And so if we have, right, so this is an example of using our standard hydrogen electrode. The potential for, here we have a zinc standard hydrogen electrode. This is an example of how we measured the cell potential for, or the absolute value of this reaction, right? We've defined arbitrarily, so we just said standard hydrogen electrode is 0, right? The potential energy of our zinc system, right, we see that it moves towards, current moves towards our standard hydrogen electrode, which means that our high potential is the zinc reaction, right? It means it's higher relative to our standard, which we just set arbitrarily as 0. So scientists then devise a way to explicitly calculate this potential energy difference, which if you guys have taken electricity and magnetism, you know the current that flows through the system is then related to this potential energy difference. Is V equals IR, right? So if you know the resistance of your wire, just in case you guys are going to take this in the future, V equals IR, this is your potential energy difference. The current, you can measure the current with the amp meter, right? So that's something you just pick up from Home Depot, an amp meter, and if you know the resistance of the wire, some tabulated value for the metal, then you know your potential, right? So if you just put these two things together, you measure the current, you know the potential now. And so we know that current is moving towards the standard hydrogen electrode, which means that our relative value has to be higher than the electrode. So we just say, okay, well, that electrode value is 0, so whatever this value of potential we get has to be our standard cell potential. All right, so then our standard cell potential for the anode, which is where the oxidation reduction happens, is going to be minus 0.76 here, or plus 0.76. The sign of this is where things are going to be starting to get a little tricky, right? Because here, this is the oxidation reaction, and things are usually measured in terms of their reduction potentials, right? So this is going to be kind of annoying on exams. On the exam, I'll be very explicit about, you know, what potential you're given. The idea, though, is that if you have a oxidation reaction here, right? So we know that this is the potential coming from the anode, which is where oxidation happens. That's why we know it's an oxidation reaction. Why is this sign reversed? Well, you know that if you're measuring the reduction potential, which is just the opposite of this reaction, right? Whenever we flip a reaction around, all we do is we just flip the sign, right? So the same way for when we're looking at delta G for a reaction, if you have delta G of the forward reaction positive, meaning it's a non-spontaneous process, then the reverse reaction is spontaneous because it's the negative value of delta G. So it's the same thing with the potential. So the reason the sign flips is because this is an oxidation potential, which is the reverse of reduction potential. And in tables, or you're gonna have to look up tabulated values of this, usually things are always given in reduction potentials, which I know, you know, there's negative signs, positive, minus, oxidation, reduction, anode, cathode, direction of current, direction of electron flow. These are all going to be flowing in different directions, right? So this is one of the ways that we have to be careful when we're treating these systems. And I acknowledge that it seems unnecessarily complicated with all these positive and minus signs, right? Because this is actually significant. If you get the sign wrong, then it tells you that, oh, this is not a spontaneous process when it might actually be a spontaneous process. Right? But this is how it's actually measured, right? We just set hydrogen electrode as a value for 0. What about if we have a copper example, right? So the copper example, the standard potential, we have the electron, so the current is going to be flowing from the anode to the cathode, right? That's a non-spontaneous process, which means that current is actually going to be flowing from the opposite direction, right? Current electrons are going to flow from here down to here. And so because this value is lower in potential, right, potential energy, then the electrons are going to flow towards the lower potential energy. And again, we're looking at an oxidation potential here, right? Which means that the reverse, which is usually what's measured, is going to be the negative of that. So the standard cell potential here for it would be the cathode in this case, so the picture kind of has things backward, would be minus 0.34 volts. And again, volts is just the unit of electrical potential. And volt is something that you can convert into joules, right? So volt is a unit of energy, you can convert it into joules. And so, like I said, the values that you see tabulated are always the reduction potentials, right? So we say the standard hydrogen electrode is a zero value, we just set that arbitrarily. Everything else here, we're looking at the reduction potential, which means that if we put it in an electrode and we see that the current flows from the hydrogen electrode to, let's say, a tin system, then we actually measure a positive potential from that system. But we know that that just means that the opposite reaction is happening, so we flip the sign and just set that as a negative value relative to the standard hydrogen electrode. So as we go up, these are going to be more easily reduced because they have a larger reduction potential, right? They have a larger difference in potential, so they're going to be more easily reduced. And they're going to be stronger oxidizing agents, meaning if you put them in a system with another metal, they're going to oxidize the other metal because they're going to pull the electrons. They're saying we're a more active metal, we're going to pull the electrons off of you, even if they're just connected by a current carrying wire, right? And then we have the opposite trend, right? These are going to be more easily oxidized, right? More readily give up their electrons, and these are going to be stronger reducing agents. So these are the values you actually see. So the important thing when you're looking at cell potentials, right, is you're going to be comparing these values, but you're going to have to understand that some of these are going to have to be flipped because they're standard reduction potentials. And there's kind of two equations that you'll see that are related to these values, right? And so if we want to calculate the standard electric potential, we have to just make sure we're keeping track. So I'm going to show you some steps, but you just want to make sure you keep track of whether the anode or cathode, and it's really the anode that's important, are oxidation or reduction potentials. And the reason that that's so important is depending on if it's an oxidation or reduction potential, it tells you how to use that potential value differently. Right, and really it's going to come down to, are you going to use that the cell is the addition of the cathode plus the anode, or you'll define it, the cell, as the subtraction of the final state minus the initial state. Anode. Right, so which one you use just depends on the potential values you're given to you. If you're just looking up reduction potentials, you'll always use this one, the reduction potentials. If you're given mixed oxidation and reduction potentials, you use the first one. But you always have to set one as a positive value, or the absolute value for one. All right, so combining a little bit of everything that we've talked about so far, you're going to identify first the oxidized and reduced species. So,
could you go back to this?
yeah,
I'm sorry.
you're going to identify the oxidized and reduced species, which is, given the standard cell notation or the specific redox reaction, right? Both of those, you'd be able to identify what's oxidized and what's reduced. Then you either look up the standard reduction potentials or you're given the reduction and oxidation potentials. Once you have both of those, then you just look at the difference between those potentials, and that gives you the new potential difference in your cell. Why is that potential difference important? Well, the value of that potential difference and the sign of that potential difference tells you whether it's spontaneous, right? If the potential difference is positive, it's going to be a spontaneous flow from high to low electrons. If the potential difference is negative, it's going to be a non-spontaneous process, which means the reverse redox reaction is more possible. Good? All right, add the two half reactions together, obtain the overall redox reaction. This is just to give you the overall redox reaction. And then you add the two cell potentials obtained in step 2, and this is only if it's mixed oxidation and reduction potentials. This is just what I wrote on the previous page. All right, if it's not mixed oxidation and reduction potentials, you're just looking at oxidation potentials, then you just use the subtraction. And honestly, I think this is a little bit simpler, is equal to E cathode minus E anode. Right, and again, these values represent the difference from the standard hydrogen electrode. That's our common differentiating factor there. Okay, so am I good to go on to the next? Still writing? So here's an example. This one is an oxidation potential. We have a mixed oxidation potential. This is a reduction potential. So to calculate the standard potential for this cell, we have the cathode plus the potential of the anode, right? And the reason that we use this version is because we're given a mixed potential, right? This one is an oxidation potential, and this one is a reduction potential. And so just plugging these values in, you have 0.40 volts plus minus 0.14 volts. And that gives you 0.26 volts is the standard cell potential now. And so the standard cell potential is saying that, well, this is going to be lower in potential value. It's going to be a more positive value than the anode, right? The anode is a large negative value. So the potential is going to move from high to low, which is what gives us a positive sign. So this is greater than 0, which means this will be a spontaneous reaction. What is it? And it might seem a little counterintuitive, but if we think about the Gibbs free energy as well, right now we're looking at how does this result in direct flow, right, of the electrons. If we have a reduction potential or an oxidation potential that is positive, right, that corresponds to a negative reduction potential, right, which means that this is a larger it's a more positive number than negative 0.4, right? If we were comparing reduction of both of these, right? If we flip this reaction around, this would be a negative value. right? So if this was a negative value, this would be lower in energy, right? It would be a more negative number than this one, so that's why we know that this reaction flows down there. So that means that this is a spontaneous process. The way we've defined it in terms of the standard hydrogen electrode means that this positive value is going to give us a spontaneous process for the cell potential. But this is more of just analyzing the potentials rather than looking at thermodynamics and free energy. This is saying the same way we know a ball rolls down a hill, except we're looking at electric potential, not mechanical potential energy, right? So this is the same idea with that. We're going to relate that then to the free energy of the system, right? Because we don't have to understand thermodynamics at all at this point. We're just saying which direction our electron's going to move. And the realization is that the direction electrons move corresponds to the reaction happening, because the reaction is what generates electrons and what takes electrons, right? And so again, just to summarize, the cell potential that's positive indicates a spontaneous reaction, right? So we indicate a spontaneous reaction with a positive standard cell potential, right? It's because the oxidation potential is really the negative of the reduction potential. So we compare the two reduction potentials, whichever one is more negative tells us the spontaneous direction of flow, right? So if we move towards the, from high potential to low potential, that corresponds to a positive overall cell potential, right? And we're moving from the anode to the cathode. Okay, and so if we look at another system, here we have iodine and copper. We're given two values. Again, this is the oxidation potential here. In the lab today, we'll talk about using just only reduction potentials. This is a reduction potential. So when we do E cell, we get E cathode plus E anode, right? The cathode is where reduction happens, which is the first potential, which is an reduction potential. So this is going to be 0.54 plus 0.34, which gives us a potential of 0.20 volts, right? So now this would be a non-spontaneous process, so the current would actually go in the opposite direction. And again, we're moving from a large potential to a smaller potential, which is why current flows in that direction, and it corresponds to spontaneity or non-spontaneity. If we were to look up tabulated values, this here would be reversed, and so we do the two values subtracted from each other, or this would be reversed. If you're comparing two oxidation potentials, and you would still get the same answer. It just depends on which sign you would have to reverse. Okay, so briefly in lab, we're going to talk about then the relationship between all of these, right? A positive standard potential, like we said, corresponds to a spontaneous reaction, because we know we're going to have spontaneous movement of electrons, right? The same way we do just in standard electricity and magnetism. And we know that spontaneity is related to delta G. So we're going to come up with a relationship between delta G and the standard cell potential. We know delta G is also related to the equilibrium constant, so then these are all going to be related to each other somehow. Delta G is related to K, right? The standard delta G of reaction was equal to minus RT ln times the equilibrium constant, right? This is how we plotted our data when we just plugged in delta S and delta H for our reaction last week. These two are related by this relationship. Alright, so you can go back and forth, you can solve for K by, exponentiating both sides. That gives you something like the Arrhenius factor. Right, if you solve for K, you get K is equal to e to the minus delta G of reaction over RT. Right, remember for kinetics, the speed of the reaction is related to the activation energy. In thermodynamics, the value of the equilibrium constant is related to the change in free energy of the system. And so we're going to come up with a sign between the two. And this gives us something that connects equilibrium, thermodynamics, and our redox reactions now, right? For a spontaneous process, we know delta G is negative. For a spontaneous process, we also know that this cell potential has to be positive because that tells us the direction of movement of electrons. And we know that if the equilibrium constant is larger or smaller than 1, that also tells us what we're going to favor, products or reactants, which in this case involves the movement of electrons in this case. All right, so that's how we can qualitatively interpret all of these things. All right, so I'm going to stop right there.